I want to thank everybody for coming today and thank Marianne for inviting me to talk about chip-based epigenetic analysis. What I wanted to do today was really give you an overview of chip-based technologies and how they're being used. Just start off with discussing just an overview of epigenetic modifications, and then talk about how chip-based technologies evolved, how they're being used in epigenetics, delve a little into the methodology. Didn't want to get too far into the methods, but give you an overview of the methods being used, and then talk about how things are transitioning into next-gen sequencing, which I'm sure everybody's aware that sequencing is really where the whole field is going towards, and some of the methods that are coming out now, such as PatChip, that are really pushing the epigenetics field forward. And then just at the end, touch on antibodies, since all of these chip-based technologies really are based on antibodies, and that's really the key to getting them to work. I think everybody knows that identifying promoter interactions and epigenetic modifications, sites of methylation really are crucial tools that have come out recently for looking at and decoding key disease pathways, doing biomarker discovery, drug development. It's really a booming field, and it's centering upon looking at DNA methylation in the promoter and upstream regions, as well as looking at histone modifications involving histone methylation and histone deacetylation in terms of modifying histones, changing the chromatin structure, and affecting gene expression. I'm sure most people are aware that DNA methylation occurs at the cytosine residues. In vertebrates, only about 3% of cytosines are methylated, and it's generally occurring in CPG islands, which are found upstream of promoter regions. And in conjunction with DNA methylation, there's histone modifications going on, both, as I mentioned before, methylation and acetylation, and these two work in conjunction, resulting in changing the conformation of chromatin, where chromatin is in a switched-on position. It's in an open architecture where DNA is generally unmethylated, and histones are acetylated. That lets genes be transcribed and gene expression occurs. And things then shift into a closed architecture where DNA methylation is occurring in the promoter regions, as well as methylation of the histones and deacetylation of histones in general. So it's really this opening and closing of the chromatin structure that's affecting gene expression, and methylation and acetylation are the controlling factors that people are looking at in epigenetics. And there's a variety of different factors that are regulating this methylation and acetylation. And some of these I'm sure Michelle will talk about. Methyl binding protein is involved in methylation, as well as the methyl transferases. And with acetylation, there are HDACs. There are several HDACs are actually have been turned into therapeutic drugs that are approved now, as well as histone transferases. And these are really the key factors that are shifting between the active and the inactive chromatin and turning gene expression on and off.